Welcome to the Bentley tutorial series for Engineers Without Borders USA. This presentation will review modeling pipe flow. This presentation will review the expectations of the preliminary community assessment, some common properties and basic modeling components of pipe networks, and also demonstrate basic pipe flow models in Flowmaster and WaterGems. Engineers Without Borders has published Water Resources Guidelines for chapters working on water projects. The document provides basic elements for making informed decisions throughout the project. It is accessible from the Engineers Without Borders homepage at ewbusa.org. The guidelines recommend conducting a baseline survey or preliminary assessment, which is best done before modeling. The initial survey should determine the community's needs, identify the water source, assess the source's water quality, and collect data on demands. Also, the engineer should understand the performance of any existing water delivery systems before embarking on designing improvements. That includes collecting as much physical data as possible, describing size of current pipes, tanks, and other features. Keep in mind that measurements and field assessments should be taken carefully to ensure a high-quality design. Work with communities to understand what materials, parts, or features are needed to sustain the system. It is crucial for the final design to express any benefits of improvements that are to be made. This is where WaterGems can help quantify and visualize benefits of a new or improved design system. Once you have assessed your existing system, you will want to determine the details of the pipes in the distribution network. You will enter as much existing data as possible to accurately represent your system. The majority of networks considered for EWB projects are usually such that the pipe diameters of 150 millimeters, which is about 6 inches, are the largest encountered. Pipes should be sized so that they can consistently meet the assessed demands. And keep in mind that domestic water demands in the developing world are typically much lower than in the US, so adequate velocities might need to be achieved by reducing the pipe diameter to smaller than usual. You can use your WaterGems model to evaluate performance of different materials in your system. Plastic pipes, including PVC and HDPE, are common because they're typically cheapest and have good performance. Plastic pipes are comparably lightweight, immune to corrosion, resistant to abrasives, and available in many countries around the world. Galvanized iron, or GI pipe, is used in cases where large pressures are expected. However, it is heavier and more expensive than plastic. Engineers Without Borders suggest that the selection of materials should include an assessment of market constraints, like performance, price, and availability. Ultimately, the choice depends on the community's needs and individual design. In practice, pipe networks consist of much more than pipes, including fittings, tanks, reservoirs, and pumps. For our modeling purposes, these elements are categorized into 4 different groups. Links, like pipes, are connected to junctions or boundaries. Junction nodes represent a specific point in the system where an event of interest is occurring. Junctions include points where pipes intersect, points where major demands on the systems are located, or critical points on the system where pressures are important for analytical purposes. Boundary nodes are points in the system where the hydraulic grade line is known. They include tanks, reservoirs, and pressure sources. A model must contain at least one boundary node for the hydraulic grade lines and pressures to be calculated. Pumps and valves share properties of both nodes and links. They occupy a single point in space and also are nodes where head changes can occur. Now we'll walk through a pipe flow problem using Flowmaster. Flowmaster is designed to be simple yet powerful to help you quickly perform hydraulic calculations. Start by creating a new project and a new worksheet by clicking on the page icon at the top left. Flowmaster can be used for calculations with open channels, weirs, and inlets. Since we're dealing with water distribution systems, we will choose pressure pipes. You can see on the left-hand side here, we have properties defined by the user where you enter values for pressure, elevation, or length. You choose the property at the top for Flowmaster to solve for, and also specify a friction method. The units are listed to the right of each text box. You can change the units by right-clicking on them. The discharge units are now feet cubed per second. Let's reset them to liters per second. Now we'll do an example pressure pipe calculation, which I have already set up. Set the worksheet to solve for discharge. For the friction method, choose Hayes and Williams formula. Start by making a pipe with a length of 3,000 meters and a diameter of 200 millimeters, which is a little less than 8 inches. Use the material library to choose a roughness coefficient. This 150 is for PVC pipes. Set elevation 1 to 110 meters and the elevation 2 to 100 meters, so the pipe is sloping downward from 1 to 2. Then solve for discharge by clicking the icon with the green arrows. Notice the value calculated for discharge. It is 27 liters per second. Let's make the diameter smaller and change it to 150 millimeters. And solve again. Notice the flow decreases significantly from 27 liters per second to 13 liters per second. To get a visual representation of this pipe, go to Analysis, then Profile. In our case, the elevation difference is only 10 meters compared to the length of 3,000 meters, so we're going to manually scale the aspect ratio to be smaller in order to better visualize the slope. Here we have the profile. We can keep it open at the bottom because it will update with new inputs. We can close the Project Explorer to make some space. Now change the worksheet to solve for elevation at 1. Using the same flow calculated before, let's increase the pipe diameter back to 200 millimeters and find out what elevation would be needed to get the same discharge volume. We can look at the new pipe profile to compare. When the pipe diameter was smaller, the elevation difference was 10 meters to achieve the same flow. Now, with the larger diameter, the elevation difference is decreased to less than 3 meters. See how head loss is required to drive flow when the pipe diameter is bigger. This demonstration was to show you with calculations how flow was defined by head loss, and how easy it is to use Flowmaster to solve simple pipe flow problems. Now we're going to construct the same type of pipe in water gems. We have a project open in water gems, and we will start with building a simple network to show the same things we calculated in Flowmaster. I'm adding 2 reservoirs connected by a pipe. Reservoirs are a type of storage node, similar to tanks, but unique in that the water surface elevation of a reservoir does not change during an extended period simulation. We can add elevation to our reservoirs. We'll add the same dimensions from Flowmaster, with the first reservoir at a higher elevation of 110 meters, and the second one at 100 meters. Now for the pipe, you don't need to enter any elevation data. If you click on the pipe properties, notice the pipe has R1 as its start node and R2 as its stop node. The pipes will be associated with the elevation data for the nodes that they're connected to. We will, however, modify some of the pipe's other properties. For the pipe lengths, I mentioned earlier that they're automatically scaled based on the drawing. We want to change ours and assign a user-defined length. We're going to make the length 3,000 meters. For the pipe diameter, we'll make it 200 millimeters. And we'll change the material to PVC. Note that any system you make in water gems must have at least one junction to be a functioning system. So we will add 2 junctions, one at each end of the pipe. Earlier I described junctions. More specifically, junctions are non-storage nodes where water can leave the network to satisfy demands or enter the network as inflow. If you look at the junction properties, you can see they take on the characteristics assigned to the location where they're placed in the drawing. So both of these junctions will have elevations between 110 and 100 meters already assigned. To see the profile view of the system we just made, go to View, then Profiles. Click the page icon to create a new one. And we want to select from our drawing. Make sure we get our reservoirs in both of our junctions. You can see it starts at R1 and ends at R2, which is what we want, so you can go ahead and open the profile. The Profile Series options appears. This is where you can add other data to the graph by checking any of the boxes. We're going to make sure only elevation is displayed. And there's our profile graph. As for the display itself, the chart is very customizable. To view, you can click on the Chart Options icon or right-click on the chart and select Chart Options. To change the whole look of the graph, you can choose from the themes. There are several to choose from. I like grayscale, so we'll use that. The chart has a range of options, so you can really tweak it to make it fit your needs. If you prefer results in table form, you can click on the Data tab. We'll save this profile window to view later by minimizing it. Okay, now we're ready to run our steady state simulation, so we can determine the flow volume through the pipe. A steady state simulation computes the state of a system, assuming that hydraulic demands and boundary conditions do not change with respect to time. Computing these steady state simulations is important as they are the building blocks for the EPS or extended period simulations. The previous tutorial explains the different methods of calculating friction losses, and just now we set Flowmaster to follow the Hayes and Williams formula for friction losses. Now that we're in water gems, the default calculation method is Hayes and Williams. If you want to change it, go to Analysis and Calculation Options. Double-click on the Steady State Base Calculation options. If you look under Friction Method, you can select from this menu. To compute, make sure the base scenario is selected, and then go ahead and click the green Compute arrow. If you notice on the drawing, flow arrows appear in the direction that the flow is moving, which helps you visualize your system. Now if we look at the calculation summary, for the steady state simulation, there's only one time step. If you look over to the right column, for our system, the flow is 28 liters per second, which is the same discharge value we calculated in Flowmaster for this system. Hopefully this gave you a good idea of how to use Flowmaster and water gems for pipe flow modeling. Now we'll go through some assessment questions for review. The preliminary assessment should consist of all but which of the following: A. Identifying the water source. B. Collecting demand data. C. Evaluating existing collection and distribution system. Or D. Quantifying and displaying system improvements. And the answer is D. The preliminary assessment is for collecting data. The water gems model can help with quantifying your system's improvements. Number 2. Domestic water demands in the developing world are typically much lower than in the US, so adequate velocities might need to be achieved by blank pipe diameters. A. Increasing, B. Decreasing, or C. Measuring. And the answer is B. Decreasing pipe diameters. Number 3. True or false? In water gems, the user is able to change the friction formula used in calculations. And the answer is true. The friction method can be set to Darcy-Weisbach, Hayes and Williams, or Manning's. Thank you for watching, and please join us for the next tutorial.